This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Thank you for coming, everybody. First of all, before we start, I would like to acknowledge the country. The University of Melbourne acknowledges the traditional owners, elders, and knowledge holders of the unceded lands on which we work, learn, and live. The Wurundjeri Woi-wurrung Bunurong peoples, so Burnley, Fisherman's Bend, Parkville, South Lake, Werribee campuses, the Yorta Yorta Nation, Dookie and Shepparton campuses, and the Dja Dja Wurrung people will recognise a unique place held by Aboriginal and Torres Strait Islander peoples as the original owners and custodians of the lands and waterways across our continent, with histories of continuous connection dating back more than 60,000 years. We also acknowledge their enduring cultural practices of caring for country. We pay respect to elders past, present, and future, and acknowledge the importance of Indigenous cultures in the Academy. As a community of researchers, teachers, professional staff and students, we are privileged to work and learn every day with Indigenous colleagues and partners. Thank you so much for coming today. I'm super excited to introduce you to Professor Rachel Webster. Rachel Webster is actually my now ex-supervisor for my PhD thesis, but we have a relationship that goes back 11 years because that's how long it took me to do my PhD. Rachel has to be one of the most patient people, I think, and driven as well. So Rachel is a bit like me. She has her fingers in many, many pies. Extraordinarily good at astro, not even just one area of astro. I think you do like gravitational microlensing, quasars, you're into cosmology. What else do you do? Radio waves, everything. Rachel's done it. So she's an absolute juggernaut of the astrophysical world, but also has her feet firmly planted on the earth, and has always been interested in, always 10, 20 years or so, you've been working on this sort of project on how we can use physics basically to improve our sustainability in our lives on Earth. And this project, I'm sure Rachel will tell you a bit more about the Latrobe Valley project, but I actually haven't heard a huge amount about it myself, so I'm super, super excited about tonight's talk. Please welcome Professor Rachel Webster.
Okay, so thank you very much, Claire. All PhD students are valuable, let me tell you. So we do like to make sure that they all finish, no matter how long it takes. Okay, so this evening I'm going to be talking about something I don't often talk to broad audiences about, which is energy, and in particular geothermal energy. And I want to assure you that I'm not going to cover the detailed syllabus from the VCE, because I assume you've all got, well, in fact, I know you've all got excellent physics teachers who are going to go through the details of that with you. But what I want to do instead is to talk around energy and the challenges that we're facing with energy, and where we could, or where we might be heading and where we could head, and really encourage you to think about our energy future in a really global way, because the challenges are considerable, and I don't think any of us really know the answer at this point in time. So it's in particular going to be up to the younger people to sort their way through it and lead us hopefully to a more sustainable sort of place. So, and as Claire said, I've been working on geothermal energy really for about 15 years now. It's sort of my, I think you're saying it's not my daytime job, but I'm an astronomer, so maybe it's not my nighttime job. I don't know quite how you express this. So I'm going to talk to you a bit about geothermal energy. Well, I'm going to talk to you generally about the context that I think about this in, and then talk to you in some detail about geothermal energy and what we're doing. So just to give you an outline, I'm going to make a few comments. I'm going to talk about, how I understand renewable versus sustainable versus no carbon dioxide. Talk a little bit about electricity, power and heat as it applies broadly in Australia. Then talk about geothermal. What is geothermal? Why do we care about geothermal, particularly in the Latrobe Valley? what's happening internationally, and we'll just sort of see how we go. We've got a reasonably small group of people here today, so I am really comfortable as we go along. If you want to comment, you know, stop me, whatever, because I think, you know, I think that would be quite appropriate. So don't hesitate if I go somewhere and you think you want to ask something about it. Okay, so I'm going to start just by sort of framing the issues, and I roughly think of this with three different buckets. So it's partly about money. We'll go there in a moment. It's partly about technology, and it's partly about sustainability. And this problem is so difficult because it's all three of those things, and they interact in lots of different ways. So, for example, around the money, the question that is mostly being asked is, can we get the cost down? Can we keep the cost at a minimum? And from where I sit basically at the moment, I would say the answer to that is actually no. And that is hard because people want to see their energy costs go down. But the alternative to not actually facing up to this and addressing the problems is that we will have things happening, you know, in our environment, which will cost us an awful lot more than it would cost us to actually resolve these problems for energy. And so it's not a question of can we do it for less, it's a question of weighing up the alternative routes that we've got in the future and which one then is going to be the least damaging, if that makes sense to you. Around technology, we've got existing technologies, and then we've got technologies that may still need to be determined. So under mature technologies, obviously solar and wind and hydro, we all know about those, and we've got quite a lot of those. There is nuclear fission, of course, not in Australia at the moment, and large nuclear fission is a proven technology, expensive but proven. Biomass is a proven technology, not widely adopted again in Australia. And then in geothermal, I've got D and E. D stands for direct geothermal, which I'm going to talk more about, and E is electricity generation. And one of the distinctions I want to make tonight is that not all energy is electricity, and there's considerable point in starting to think in a much more sophisticated way about the energy that we use. Emerging, well, of course, there's nuclear fusion. We've spent billions and billions and billions, not in Australia, but elsewhere in the world, trying to get nuclear fusion to work. If it worked, we'd be home and hosed. It's not promising even yet, and we're still spending billions and billions. So it's there, though. There's carbon capture and storage, which we have spent, Australia has spent billions on. It's not something that gets me very excited. I think that it's probably a technology that, if it can work, will be extremely expensive. And then I've also got geothermal, the generation of electricity from geothermal down here as well, because there are new technologies coming onto the market. Then there's renewable versus sustainable versus low carbon dioxide. And these are actually not all quite the same. And as I sort of discuss some of these, I want to draw the distinctions, which are sometimes a little subtle, but it really does depend on what questions you're trying to answer, exactly where you go with each of these. But the thing that I think is very clear is we require new energy infrastructure, and I guess that's obvious to everyone, particularly in Victoria. Our coal-fired power stations are going to close down, and so what's the best choice? And that's not an easy question to answer. Okay, so as I say here, these are all complex interconnected issues, but what I would argue really strongly is that if we put good science into the mix, then we can improve the outcomes. And sometimes a lot of what comes out is political posturing, dare I say it, rather than really trying to address the good science that we may be able to use to impact this. Okay, so what does sustainable mean? Well, I've written down two definitions here, one for renewable energy and one for sustainable energy. And let's start with the renewable energy. It's energy from a source that is not depleted when it's used, such as wind or solar. Now, obviously, if we take billion-year timescales, they do get depleted, but we'll come to that a bit more in a moment. Sustainable is an energy source that doesn't compromise future generations. And you'll see that there's, quite a subtle difference between those two. And I hope I'll make that clear as in the next few slides. But let's just start with renewable energy sources. So in that bucket, I've got 1, 2, 3 there. So there's fusion, which is from the sun. So we've got a star relatively close by. It is turning hydrogen into helium. It's producing an enormous amount of energy, some of which falls on the Earth, a very small fraction of which falls on the Earth. Now, fusion or that solar energy actually manifests itself directly as solar. So your photovoltaic cells will pick that up. It's actually quite a low impact on the surface of the planet. It's incredibly important, but it's not a high energy intensity. We convert it as much of it as we can. I think the best numbers at the moment are getting close to 30% of the energy that falls on a solar cell can be converted into electricity. But it also warms the atmosphere of the planet. That turns into wind energy. The evaporation of water, does your hydroelectric energy. You grow plants, that's your biomass. And of course, if you take all of that, you can turn it into green hydrogen. So all of those are rely on the electromagnetic radiation that's coming from the sun. So in essence, they're derivatives of that solar energy. The second sort of energy, so these are the sort of the basic ones that we have available to us, is energy that comes from the core of the Earth. And that is actually due to fission. So that's radioactive elements that are actually, breaking up and releasing energy such as uranium and so on. And so we have a very hot core at the center of the Earth. So I like saying that this is the biggest nuclear reactor of all, and yet we're delightfully shielded from it, of course, and it will keep going for a very long time as far as we know. That heat travels up through from the core of the Earth through to the surface, and we can access that. And then the final one is tidal, which is obviously gravitational largely due to the interaction between the moon and the Earth. Sun gets in on the act a little bit. In fact, the diagram that I have put up there isn't quite how it works. I've just been lecturing on this to my first years. But anyway, the basic idea is that there's movement of the oceans, and if you can devise a mechanical method for using that flow of water in some regions of the Earth to run a generator, then you can turn that into electricity. That's probably mostly one of the more difficult ones to do, but it is done in some locations. So the last thing that I've got on the slide there is timescales. And sometimes people forget to think about timescales when they're thinking about generating energy. Are we trying to solve a problem on a 3-year timescale? That's the sort of election cycle. Are we solving it on the timescale of our adult lives? So, there's a solution for me, but I'm not going to worry about the next generation. Or are we trying to solve it on a really long timescale where in thousands of years' time, they'll be able to access energy in exactly the same way that we do now? So that is actually a really important question, because a lot of the infrastructure that we build today only has a finite lifetime. So, we build Snowy 2. What's the lifetime of a big dam? Well, it might be 100 years. It's not much longer than 100 years. The infrastructure, the actual structure of the dam only lasts for a certain period of time. What happens then? And so in thinking about all of these solutions, the politicians are happy to cut a blue ribbon. It's working today. I don't need to worry tomorrow because I'm not going to be Prime Minister. But if you're thinking really about solving these problems, a very long-term perspective is kind of where you need to be. Now, of course, the bottom line is we don't have that luxury. You know, if we could wave a magic wand and solve the problem on 1,000-year timescales, we'd be doing it. But it's something that you need to keep in mind as you sort of work through actually building infrastructure and thinking about the resources you use. Okay, that's about renewable. Now let's think about sustainable. And I have a slightly different definition of this that I'm going to bring in, which is because in my mind, one of the greatest problems that we're facing is, in fact, the warming of our atmosphere and all the implications that can come from that. For me, sustainable means preserving the atmospheric temperatures of the Earth within a narrow band, you know, which we're probably right on the edge of exceeding at the moment, but forever. In other words, are we going to do something that is going to tip us over that edge? And I've got a very sort of bizarre example that I'm going to give here, but you know, let me just show you. This is a report. It's the Port Phillip Bay Coastal Hazard Assessment, right? So we all live on Port Phillip Bay or not far from it. And this is a really interesting report if you haven't actually gone in and read it. But what it does is it actually works out what will happen to around Port Phillip Bay as basically as sea levels rise. It's something I get my students to think about quite a lot. Sea levels will rise. They have already risen and they're going to go up quite a lot more. And the numbers that I've put in front of you are for about a 0.8 metre sea level rise. This is actually quite modest in terms of what could happen on the timescale of some of the younger members of the audience that I see here. But just to give you the sort of modelling that has been done, on the left-hand side there, it's the fraction of the Port Phillip local government area, so that's St Kilda and places around there, that would be underwater as a function of sea level rise. And in case you can't see the numbers along here, so at let's go to 1.4 metres, it's about half of the Port Phillip local government area. These are calculations I get my students to do because, so basically, you know, you don't have to melt very much of the Greenland's ice or the Antarctic ice to get 1 metre. And so I encourage them not to buy houses down close to Port Phillip Bay. If you're going to invest in real estate, in fact, the number to keep in mind, just so that you know, is about 80 metres. So melt all the ice on the planet and the water levels will go up 80 metres. So you're pretty safe if you buy above 80 metres. That's not a lot of Melbourne, I think. So just something to keep in mind though. And the second image there just shows you some of the areas that are most at risk. But again, you know, these are, I mean, this is but one tiny example of the sorts of impacts that the decisions that we make about energy are going to have on how we live. Okay, so it's a very complex problem. It's a very complex problem. Now, the next thing that I wanted to introduce is, so, you know, when we come to make decisions about things, there are many metrics that we can use that guide our decision making. One of them is, how much is my electricity bill going to be? And I've already said that I think, you know, we really need to just bite the bullet and recognise that, you know, we will pay more. Okay, and if we're going to get an infrastructure that is actually going to prevent some other serious things from happening, such as the sea level rises that I just showed you. So, one of the metrics that you can use as far as energy is concerned, it's, you know, usually they look at something called LCOE, which is the levelized cost of electricity, okay, and which is basically taking everything that you pay into account, how much is a kilowatt hour going to cost. So this is something quite different. So this says, how much carbon dioxide am I going to release for each kilowatt hour that I actually use? And it's a life cycle assessment. And so what it starts to say is, instead of just thinking about, well, you know, I dug up a little lump of coal and I put it in a generator, it generated, you know, a little bit of electricity, that's the entire story. Instead, we say, okay, how much carbon dioxide was released in building the whole of the plant that generated that electricity? There's also obviously the running cost, so that's, you know, how much coal we put in there, but also how much carbon dioxide are we going to generate to get rid of the infrastructure that we actually put in place, because it's not going to last forever. And that obviously varies depending a lot on the resource that you're actually looking at. So you can see there's the upstream, so that's extracting the resource, getting it to wherever it's going to be used. There's the fuel cycle, there's the operation, there's downstream. So it's basically taking into account everything to do with generation of electricity. And so, and the numbers that I'm quoting here are from something called the National Renewable Energy Laboratory in Colorado in the USA. So there's not a lot of people who are actually doing this work, but they're a reasonably august body. And this is a graph from them. And so what they're working out is grams of carbon dioxide released per kilowatt hour. And it's not quite the way I would do this study, but what they've done is they've gone to the literature and they've taken everybody who worked this out, and then they've worked out an average value and then a range that covered most of the values. And you'll see in this plot that, our favorite friends over here, gas, oil, and coal, are all generate a lot of carbon dioxide for every kilowatt hour that's produced. That doesn't come as a surprise to anybody, because we know that that's the issue that we're sort of facing. But it then works out all the others as well. I've circled geothermal energy, which is what I'm going to talk to you a little bit about. But you see the pumped hydro is actually has quite high emissions, and that's compared to some of the other renewables, and that's simply because you're building a big infrastructure that in fact releases a lot of carbon dioxide in its construction. Once it's operating, it does very well, but if you take the whole life cycle into account, then you've got that release of carbon dioxide. So it's about thinking very carefully about the metrics that you're using to evaluate these projects, and understanding what you think the bottom line is. And just to go back to where I started, I'm very clear that the bottom line is we want to get carbon dioxide, or we don't want to hugely increase the carbon dioxide in the atmosphere, because that's the thing that's going to really stuff us up, okay? It's not great, I know, if your energy bill goes up, but the carbon dioxide will ultimately cost the community way, way more. Okay, the next thing that I thought might be useful, and you guys may know all of this, but again, because in my astrophysics classes, you'll be pleased to know, I make my third-year students learn all this stuff. I think it's really important to understand some numbers. How much electricity generation does Victoria need? How much electricity do I use as a household? Do you know these numbers? So do you know the scale of the problem that we're talking about? And so the next few slides that I want to show you just gives you some round numbers so that you have a feel for what's important, how much do we need, how are we going, where are we heading? And I have actually on this slide got Victoria's energy targets. I'm not going to go through that because these are just numbers, but basically, this is Victoria trying to come to grips with what's going to happen when they turn the coal-fired power stations off. In other words, how much new stuff, how much new infrastructure do they actually have to produce? And I've got this graph here, and I have to say that I am somewhat amused by this, because it starts at 2023, 2024, so that's pretty much now, and it goes up to 2050. And to say that I think this is transformed would be an understatement. But what it does show is if you try and do this, what is the magnitude of the task that you're facing? Okay, and so this is what we look like today. So this is the brown coal, this brown bit down here, and then what you'll see is there's almost as much PV generating generation capacity on the roofs of people's houses and on the large solar farms. So that's actually really quite interesting. And so we've got about 20,000 megawatts, or that's about 20 gigawatts of generation capacity. So the number that you need to know is for continuous generation capacity in Victoria, we need about 10 gigawatts. Why have we got more than that? Well, a lot of this is doesn't generate all the time. The PV on your roof doesn't generate the whole time. So there's an efficiency factor on some of the generation sources that we have. So even though you've got stuff on your roof at the moment, you know full well it's not actually generating as we go ahead. So we need about 10 overall. There's an interesting line here, which is the red line through here that you can see, and that's called, that's telling you which ones are what we call dispatchable, okay? And so that means that we have actually control over how much they generate, right? So so we don't have control over solar. It's not dispatchable. It's only when the sun shines, okay? So we can't control that energy. We can collect it and put it in battery, and then it's dispatchable, okay? But it's not dispatchable as we generate it. But you can see that they're also predicting that we need about 3 times as much generating capacity by 2050, which is actually not terribly far away when you think that you've got to actually build these things. But as I say, the number to remember is about 10 gigawatts. So this is the sort of plan that the state government has and the energy authorities. But the bottom line really is there is no silver bullet here. The expense involved in building this sort of infrastructure is actually very, very substantial, and that's what's scaring people. So let's look at this from another point of view. Let's look at, and these numbers are now for Australia, not for Victoria, but let's look at how much energy we use, and this is by household and other things. Now, this graph has got petajoules. It's an energy, well, you're all physicists here, so you know this is an energy. You may not be used to thinking in petajoules, okay? It's obviously a power of 10, but the number upstairs there is 15, okay? So it's 10 to the 15 joules, which is, so, you know, you've got megajoules, you've got gigajoules, okay? And we go up, and then we get to petajoules, which is 10 to the 15. So it's a lot of joules, okay? And what I found so interesting about this, so this is for Australia, this brown line here is what we export, okay? So in other words, we dig stuff up, so that's gas, it's uranium, it's coal, and we ship it offshore. And that vastly outweighs what we actually use, which is down here, okay? So that's also something really, really interesting just to have in mind. So let's go down to what we actually use. And this is now how we're tracking with renewables, okay? And so what you'll see here, so there are 3 basically here, because at the moment, we really only do 3 in any substantive amount. So the blue is solar, the orange is wind, and the red up the top there is hydro. The hydro is essentially not going to increase until Snowy 2 goes ahead. But both wind and particularly solar are trending upwards nicely, but they're going to have to trend up an awful lot faster. We're talking here just hundreds of petajoules, okay? So there's a long way to go to actually become all renewable. And this is now breaking down where it goes, whether it goes in manufacturing, construction, mining, you know, households or so on. You'll see why I put this slide in a minute when I start talking about geothermal, because it actually matters what we're using the energy for. It may be that the solutions for one set of use cases can be quite different from another set. You probably know already by putting PV on your roof that you've actually reduced the amount of electricity that you pull out of the grid, okay? And so that brings down the household, household consumption. It may be that we can come up with some clever things to do with manufacturing, which is a little bit what I'm going to talk to you about as I go along. So the solutions in each of these cases, transport, storage and services, it may be that, you know, for transport, we can do something different from what we might do for agricultural, forestry and fishing. So it's not just a matter of generating a whole lot of electricity and then thinking we're going to solve all our problems. We might need to do a whole lot of different things and tailor-make our solutions. But these are the 2 big ones, manufacturing and household. So if we can make an impact on those, then we're doing okay. All right, so that's my sort of introduction to, you know, sort of how I think about the problems we're facing. So I'm happy to pause for a minute there and see if there's anything before I start talking about geothermal that you might want to comment on or ask or anything else. But yeah. Green hydrogen. So what do you think about as an energy source? Okay, so green hydrogen is really interesting. Our previous chief scientist, Alan Finkel, has been very keen on green hydrogen. I have just heard in the last week that he's now decided he's not so keen. Given that he pushed it really hard. So the comment that I wanted to make about green hydrogen, and this applies to all energy forms. Again, you're all physicists, so you know that if you take an energy source and you transform it into another energy source, there's an efficiency factor, okay? You transform it again, there's another efficiency factor. So the more times you do that, and in particular for some of those transitions, the more, you know, the less you have in the end. Okay, so you might start out here with 100%, you might get down to the end with only 10% of the energy left and actually use it. Now, hydro is actually pretty good. It's about 85%, once you build the infrastructure, it's about 85% efficient to get the water up. You know, for Snowy 2, it'll be about 85% to get it back down as electricity. Okay, so that's actually quite efficient. Hydrogen, green hydrogen, is very inefficient. Okay, which also makes it very expensive. Okay, which is, I imagine, why Alan has decided that it's not going to be the future for us. What I will say about hydrogen, though, is it's a high intensity energy source. And so you can do with hydrogen what we maybe can't do with some other forms of energy. And so this is why I was saying it may depend on what you want. You're not going to use hydrogen to heat your house, okay? You don't need a high intensity energy source to heat your house. You may need a high intensity energy source to make steel, okay? And in which case you'll pay the price for making the steel because that's what you need. So it does depend on what you use. And this is where we've just got to think a lot more sensibly about what energy we actually need for what we use it for. Okay. So thank you for that question.
In regards to manufacturing, see Australia's manufacturing numbers are decreasing all the time. I know this is obviously a large component of the today, it's actually us generating. But what about the use of power to create the goods that you need if it's created overseas? This is a large environmental cost. That if our manufacturing decreases, that won't show up in any of these graphs.
Yeah, well, that manufacturing is going down, and I think that's not because they're using renewable energy. I think it's because our manufacturing is disappearing. Well, I mean, our desire for things is not going to cease. Manufactured things, and food miles. Somebody else. For a long time lived on the back of people producing things a long way away, and then we bring them to us. This is obviously not the most sustainable way of doing things. So we're going to have to think much more carefully, I think, about what we make locally, what we make in situ, what we grow in situ, because I'm going to talk about food miles in a moment, and why it makes sense to have somebody do somewhere else, right? And it really does change the equation, because up until now, it's basically been free to move stuff around. The actual transport cost hasn't been anything that we're really worried about. It will be coming into it. Okay, so it's complicated, isn't it?
Yes.
Okay, let me rattle on a bit about geothermal. So I said that I've been thinking about this for 15 years. I got into this because I was thinking about climate change. Anyway, I won't go through that full story, but the real motivation for me thinking about geothermal energy was, one, we really don't do it in Australia, and I couldn't figure out why. And secondly, there is actually a lot of geothermal energy available and therefore it seemed like it was an opportunity that we were missing. So what is geothermal energy? It's heat occurring naturally underground, which can be cost effectively carried, usually by water, to the surface for some sort of beneficial purpose. In other words, we're transporting the heat from the center of the earth up to the surface, and then we're going to use it for something or other. Now, these are just a lot of examples of geothermal heat. So this is Peninsula Hot Springs. I don't know if you've been down there. They bring hot water up, and if you go down, it's actually very pleasant to bathe down there. This is a plant in New Zealand. They have access to hot, steam that is coming out from magma very close to the surface. We don't have that in Australia, but it works quite well in New Zealand. There's another geyser that's the same sort of thing. This is the one not operating geothermal power station in Australia. It's a long story, but it's not because the technology wasn't good. This is digging a trench and putting a pipe filled with hot water for a residence or something like that, and you can use it to heat and cool a building very effectively. These are all different manifestations of geothermal energy. Okay, so just some terminology, because geothermal energy covers a whole range of things, okay? So there are heat pumps, which are basically, where you're using shallow geothermal and essentially putting, piping water down into the ground. And it's basically a heat battery. So in the summer, you put heat down into the ground, it's stored there, and then in winter, you take it out. This is widely used in Europe, okay? It could be widely used in Victoria. We have even better conditions than Europe, but we don't. We did try and get the new underground loop to be wrapped with water pipes so that every building on top of the new underground could be heated and cooled by the underground train thing. That's what they do in Europe. It would have cost a little bit more, but not a lot, because it's just water and pipes. It was a step too far for the engineers. They listened, but they just couldn't quite bring themselves to do it, which is really unfortunate. Okay, that's the heat pumps. Direct use is, and this is the one that I've been working on most over the last few years, is essentially saying, if you go to an underground aquifer, so this could be the Great Artesian Basin, or it could be the aquifer under the Latrobe Valley, or it could be the one under Perth. If you bring that hot water up to the surface, it is hot, okay? The temperature varies, as does the depth of the aquifer, but it comes up at about 85, 87 degrees centigrade from the Great Artesian Basin. It's really hot water. It's about 65 degrees from the Latrobe Valley. It's about 45 degrees across in Perth. So it depends on the aquifer. But the beauty of this is that these are shallow. And so to drill down into these aquifers doesn't cost you an arm and a leg, okay? Might cost you $1 million to get into the aquifer in the Latrobe Valley. But it's not, it's not prohibitively expensive. Those temperatures up to 100 degrees are probably not enough to efficiently generate electricity. So you've got to go deeper to get electricity. And typically there are not aquifers that far down. Now, people have thought about pushing water through, the fractures in the rocks and so on. That is not a favoured solution at the moment, but I'm going to show you where this is going now. If you can actually bring up water that is, 200 in Iceland, it's closer to 400 degrees centigrade. You can imagine in Iceland what they can do with 400 degrees centigrade water. They can generate a vast amount of electricity. And in fact, a lot of the aluminium processing is moving to Greenland for exactly this reason, because it's going to be cheap electricity there. Okay, so what this is really saying is it depends where you are, what you can get out of this process. But again, another number that you can remember is for every kilometre that I go down into the earth, the temperature on average goes up 25 C. Okay, so if I go a kilometre, it's 25 C. If I go 2 kilometres, it's 50. So if in the Latrobe Valley I go 650 metres and I get 65 degrees C, I've done well. Okay, and that's exactly the case. So, that's all and well. We've got hot water. Why do we think this is going to be interesting? Well, these are the real positives for geothermal, and this is what gets me excited. It's zero or near zero carbon emissions, and it's a fabulous replacement in many places for gas and other fossil fuels. It's reliable, so in other words, it doesn't go away. It's 24/7. And there are no storage costs. You can have it come up at exactly the rate that you want it to come up. Minimal visual environmental impact, stable and low operating costs. Basically, once you put the infrastructure in, it's free. Okay, there's almost no or very little cost involved. It's dispatchable. That means that you can turn it up and down on about a 5-minute timescale. One of the issues around power stations is once you turn them on, you've got to keep running them because it takes a couple of days to turn them off and on again. So having something that can respond to changes in demand is actually a very positive thing. Where it exists, there may be opportunities for new industries, and I'm thinking about the Latrobe Valley, and I think there's an opportunity for what I call Melbourne food bowl. So could we basically replace, all the stuff that we grow in the Werribee Plains and Cranbourne and what have you, that is getting overrun with housing, and actually put it in the Latrobe Valley. And then for electricity generation, and at the moment we're not pushing that so hard, but what it will give you is baseload power. And you will have heard people talking about using a nuclear power because they need baseload. There are other ways to get baseload, and certainly geothermal would be one of them. Now, there are some limitations, and one of them is that it's local. So, you probably don't transport it unless you generate electricity, but you're not going to transport the hot water. And so it depends on what's underneath your feet. And the big one here is there's just a huge lack of investment in the resource. And so, if they'd given us the billions that they gave carbon capture and storage, we'd be running geothermal electricity by now. So it's a frustrating scenario. Okay, let me just tell you why the Latrobe Valley is so good. And Claire, I'm looking at what the time is. There's the time. Oh, okay, we've got a few minutes more. I'm going to move fairly quickly through this now. So why is the Latrobe Valley so great? Well, it turns out that brown coal is the best insulating layer that you can put on the surface of the planet. And so underneath it, it traps heat. So in the Latrobe Valley, you have the thickest layer of brown coal on the surface of the planet. It's about 0.5 kilometre in most places. So you trap heat underneath. It's extraordinary. So leave the coal in the ground and use the heat that you trap underneath. Very straightforward. Okay, quite extraordinary. And this is a bit more technical, and I'm not going to go through it, but this shows you where it's hot. This is in the lower tertiary aquifer, but at about 0.5 kilometre to 1 kilometre. So there are two very hot regions. This map is not entirely accurate. It's what we know already. We drilled more holes, we know more, and it may be hot in other places as well. But this is what it looks like in cross section. So you can see the aquifer underneath the brown coal things. And so that's what we're looking at. Okay, so we did a study a couple of years ago because they put geothermal energy in to heat the swimming pool down at Traralgon. And so basically they didn't really know it was going to work. And so they put in a gas-fired burner as well, which is what they usually use. But they've been mostly running on the geothermal. And so we did this economic analysis, and the results I think are stunning. So it cost them 3.8 million in capital. The payback time is 5 years. The lifetime is at least 30 years. So what that means is it's been running now 2 years. So after 5 years, it'll run for free. So they'll be heating their swimming pool for nothing. It cost them in 2022 prices about 700K an annum to use gas. Okay, so you know what the price of gas has been doing since then. It's been going up and down a lot. And it's saving about 1 million kilograms of carbon carbon dioxide emissions a year. So it's a very good example. So what we took out of this And this is the sort of innovation that I would encourage you to start to think about and start developing, is could we take this idea and then turn it to industrial purposes? So that's what we've been doing for the last couple of years. And I'm not going to go through this in detail, but what we designed was what we call a Smart Geothermal Industrial Loop, which has got, in our test case, about 5 different industries on it. And we said, could we actually design this and run it down in, it's actually designed for Morwell, and we've done all the how much heat do they need and so on and so forth, and the answer is yes, we could do this and it works. We've got a lot of very enthusiastic support from local government down in Morwell for reasons that are, I guess, are pretty obvious. And so what we're now doing is we're talking to industries that could use the heat, and at the moment we're just talking about heat, not electricity, in this regime. So we could, anything below about 120 degrees, we can do. So you can see there's aquaculture, there's greenhouses, there's food drying, there's a lot of food processing that actually falls into this regime. And this is the sort of thing that I was going back and saying, it's not a matter of solving every problem, it's a matter of solving some problems, and can you make a difference with what you're doing? So, so that's where we're currently, and we're talking to bigger cheese and, people who grow tomatoes and things like that about the possibility of taking up this option. So we've designed this very carefully so that we don't actually use any water. We bring water up, we take the heat out and put the cooler water back down. And of course, it generates a cool plume when we put it back down. This is about 1 kilometre here. And this is the situation after 100 years. So in this design, so this is a real actual design, the temperature would drop 3 degrees at this production point here from the cold plume coming in after 100 years. So that's not too bad. So we're saying we can get it for you for 100 years. If you put your infrastructure here, we can make it work. So yeah, so that's where we're currently at. Now, so I'm just going to go through a couple of examples just to show you that the technology and the ideas here are not crazy, because other people are doing similar things. We're in a better situation. This is Paris. It's not the Olympic Games, but it's what's going on underneath the Olympic Games. And a significant number of households, so 250,000 households since about 1969, are heated by geothermal in Paris. You probably don't realise this when you wander around Paris. But the aquifer is called the Dogger. They have to go down a lot further than we have to go down, 1,500 to 2,000 metres. Their water comes up in the sort of same range as us. They re-inject it at 40 degrees C. It's also got a lot of mineral salts in it, which is occasionally leak because it clogs up the pipes. Our water in the Latrobe Valley is completely clean. Okay, it's not an issue. It costs them about €5 million to drill a well. Costs us about 1 million in the Latrobe Valley. So it's costed that a lot. And you can see they've got too many holes now in a small area. So that needs to be managed because the cold plumes start to interact with each other if you've got too many. The area in the Latrobe Valley is 6,000 square kilometres. So we don't need to have people getting in other people's way. All right. This is another one that I really love. This is the Netherlands, greenhouses, and this is what I think we could do in the Latrobe Valley. So that's some sort of green thing, but this is what they've got. This is run on geothermal. They're expecting by 2030, 50% of their greenhouses will run on geothermal. Various depths and temperatures, but for example, at 2,000 metres, they get 73 C. So this tells you just how good our energy is, okay? And it replaces gas. Whoops. I've done something silly there. There we go. Okay. This one I hope you like. This is fish. And this is the Werribee Plains. And on the Werribee Plains, there's a company called Mainstream. They market as Infinity Blue, and this is barramundi. And their fingerlings are grown in geothermal water on the Werribee Plains. Okay, so they bring up warm water. It's not very deep. I don't think it's even 100 metres. It's coming up at down in about little less than 30 degrees, and you can see the big vats, and that's all filled with little barramundi, which will grow into big barramundi. And if you eat barramundi, that's what you will do. Now I'm going to try and stop this. Maybe I can't. Okay, because it drives me crazy when it was when you pinch things off people's websites, you don't have a lot of choice. Now, electricity generation, this is not what we're pushing at the moment. Could we do this in the Latrobe Valley? Absolutely. It's just, it's more expensive, but it's not more expensive than the nuclear power station. So I've learned, if other people can promote nuclear power stations that are going to cost an arm and a leg, I shouldn't back off what we could do here. So this is a company, this is what they're building in Germany. And so they're going down 4.5 kilometers into hot rock. The temperatures aren't that high, it's only 150 C. We can absolutely get that in the Latrobe Valley for probably less than 4.5 kilometers. And what they do is they drill down, and because the gas and oil drillers are now so clever, they drill down and then they drill out a fan. It's a closed loop, it turns around and comes back down again. They send a fluid down and it heats up, comes up, drives the generator, and then goes back down again. It is actually, the fluid they use is carbon dioxide, believe it or not, which is fantastic. It doesn't require pumping because it's supercritical, and so it actually falls down under gravity and comes up as it gets hot and expands and pushes itself up and gets a closed system. So it's a thermocycling, that's what we call that. And then you just have an ORC at the top, and Bob's your uncle, you're generating electricity. Now, the thing about this is that technically, at 4.5 kilometers, anywhere on the planet is getting close to those temperatures. So that means it's, this is not, one of these generates a couple of megawatts, maybe 3 megawatts, but you can put it anywhere, and start to generate electricity wherever you are. All right, I'm going to finish up. So I'm an astronomer, you'd probably know that. I've worked with a guy called Graham Beardsmore, who's a fabulous geophysicist who really knows everything about this sort of stuff. I'm learning still. Regional Development Victoria and the Latrobe Valley Authority have supported us to the tune of in excess of $1 million to get this up and running. And still giving us very strong support. But what we're trying to do is get the direct use up and running, because it's an opportunity, as I've tried to explain. And the electricity generation is a potential. All right. So I think so there are my solutions. It is a very complex problem. We do need to optimize solutions. There are no silver bullets. Geothermal, I think, it's not going to solve all the problems, but it should be covered next. And it is completely unexplored in most practice. So
thank you so much, Rachel. I've actually never heard you talk on this before. You've mentioned it to me in your office as if I know everything about it, and I've never heard anything about it. So it's been amazing to hear all about that. Do you feel like a lighthearted joke?
Always.
You don't look like one. Why is wind power popular? Sorry. Why is wind power popular?
well, in some cases it's not.
I'm never asking you a joke ever again. I'm going to say knock knock, and you're like, oh. So why is wind power so popular? Because it has a lot of fans, and I'm sure you've made a few today. So thank you so much for that talk. It was energetic and powerful. Oh, I'm so funny. And I'd like to invite any questions for Rachel. If I have any from online, I've got one online, but I'll start off with in the room first. And Rachel, I'll just ask you when you receive a question from the audience, if you could just repeat it in front of your computer so that we can hear it online. So does anybody want to kick us off with a question? Oh, yeah, hello.
Hi. Supposedly your power stations are being shut off about 10-28-ish.
Yep. Oh, yeah. Maybe.
What's the level of confidence that we're going to have replacement energy supply at the market, or is that timeline just not simply true?
I mean, it's a great question. It is very problematic. I think, the power people they're not making a lot of money. I mean, that's the bottom line, and they need to invest. Most of them are getting very close to their use by date. This is what I mean about infrastructure having, it doesn't last forever. it's unclear what's going to happen. It's a really good question. I think, I mean, there's the ideal solution, and then there's how we get there. And probably the practical answer is that we have to have some bridging solutions to get to a more ideal solution. So I think that's actually what's going to happen. So what are the less than ideal solutions? Well, it's stuff like, you know, gas peaking and stuff like that. So you do want to roll out your wind and your solar. You've got to do that because they're the cheapest, but they can't operate the whole time. So you've got to have batteries and gas. And I just don't see any way around that because we've left it so late.
Grim.
Well,
It's true, it's grim.
I mean, that's the reality, isn't it, really? Yeah.
So for the talk, I really enjoyed it. I couldn't help but getting a sense of optimism. And your last line there, these opportunities need to be explored, that they will be explored like these swimming through at a local level and not require political interference. And it will evolve and spread throughout the country despite
So look, that's kind of how we're you know, it's kind of what I've been trying to do. You know, I mean, I have to tell you that I've spoken to everybody. I've spoken to the head of ARENA, the chief scientists, several generations of chief scientists. You know, it's all the way down, right? There is a very strong understanding now in the Latrobe Valley amongst regional development and the Latrobe Valley Authority, which is going to disappear, but regional development, that this is a good way to go. What we're trying to work through at the moment is to get companies to actually say, actually, we're going to bite the bullet and do it. And I would say, and you know, when I spoke to ARENA 2 years ago, they said to me, we can only fund hydrogen projects. And then when the next lot of funding came out, they can now fund geothermal. So we've been talking to ARENA, and they will put up 50% of the capital cost of any company that decides to do geothermal in the Latrobe Valley. I'm pretty confident of that now. We've had several discussions with them. So that's real progress. The other thing that happened, and this just happened last week, and this is after years, so is that it used to be that you could not get, so to get water, to extract water, you need a license in Victoria, as I'm sure you know, and you could not get a license to extract zero water. So in other words, our proposal to take it out and put it back down again so we don't bugger up the aquifer was not something I'd ever thought of. So we couldn't, we could take the water out if we could get a license, but it's fully committed in the Latrobe Valley, so you can't get one. But we couldn't put it back down because it was, once we'd taken it out, it was polluted, right? Even though we're talking about a closed loop, which the only thing we're taking out is heat, so there's no pollution, but it did not compute. So we are now over the first hurdle there, which is we can now get you can now get a license as of last week for taking out zero water and putting it back down. Okay, so that's really good. What we still have a hurdle to get over because you have to deal with many arms of government to do this. And so we've still got to get the EPA to understand that if it's a closed loop, it's a closed loop and there's no problems. But we're nearly there. We're nearly there on that. So those are the sorts of, when people haven't thought about something and it's not, you're on top of mind for politicians, you have these quite extraordinary obstacles.
Possible for an Australian beyond us to just say, I've got a bit of cash. I think I might draw a hole with Rachel.
Have you got one?
Yeah.
Yeah. I mean, please introduce me.
What I'm saying is it's not beyond the realms of possibility.
No, it's not. And look, there are little glimmerings of hope all through this, right? And obviously we've been talking about this a lot. I go on the ABC every 18 months or so. So the science show are fully behind me as well, and have another go at trying to get people to do it. And I do think if we can get a couple of pilots up, I mean, we've got the swimming pool, which is great, but if one of these companies bites the bullet and does it, I think it'll be a tsunami. You know, I really think once people understand that they can actually get their energy for free, it'll be a very attractive proposition. I mean, instead of being, you know, held hostage to gas prices, which is a set, and you know, Victorian government says gas replacement. You know, they want to replace gas. That's what we're talking about. So.
I've got a question from online, actually, from Seb1. Given, and you've probably talked about this a little bit, but if there's any more you can say, given the number of significant benefits, what in your mind are the first couple of things that need to happen to make geothermal a reality in Victoria? What are the biggest, trickiest obstacles to overcome, such as cost awareness, government support?
Yeah, well, as I say, a new industry or an existing industry to take up the opportunity would be gold as far as we're concerned. So we have the swimming pool, we have examples, but it just needs people to start doing it and to see that, you know, from a technical point of view, it's really straightforward. Look, quite frankly, it's just a bit of plumbing. It's nothing more complicated than that. You know, we obviously spend a lot of time talking to the drillers. You know, they're ready to go. It's just, you know, a couple of industries saying, "Yep, we're up for it," and we'd be off and running.
Anybody else? Yeah, please.
I keep getting ads from time to time from Australian Gas Network about renewable gas. Is that
Renewable gas.
where I feel like it's mainly a PR stuff. Are we up against someone like them or other gas companies that will push against this because, well, they have gas to sell?
What's renewable gas?
I saw the ad, I thought
Given that solar panels only absorb 30% of the energy, is there any new technologies coming through that will increase that generation?
It's almost at the physical limit already. Okay, so the solar panels on your roof don't are not 30% efficient, right? They're probably closer to 15 or 20, right? So the most efficient ones are very expensive still, but they are getting very close to the limits of the physics of the sort of cells that we currently make. Is there some other way of being more efficient? I believe the plants are more efficient than that. So if we could mimic how plants operate, we might be able to do better. But there's a limit. There's a limit. I shouldn't really say this, but a long time ago, I had an argument with David Jamieson, whom some of you will know, who said to
Series coming up.
You can ask David about this. I'm sure he won't mind. But he said to me, look, solar energy is never going to be important because, it's only, 1,400 watts a square meter that, comes from the sun. It's just not enough to be interesting in any way, shape or form. So his argument was, therefore, we have to go nuclear. Well, you know that this is not a correct argument because there's an awful lot of solar energy being generated.
Because I run a small manufacturing company and our electricity used to be around about 4,000 minutes per quarter. We put 54 solar panels on the roof and it's now got to about 300 watts a month.
Exactly. Yep.
So
It works. And if you have batteries as well, which have quite an investment, but it's actually not so hard to knock it down to actually zero. So, I mean, this is an interesting exercise for students, is to actually think about, where the break-even points are. But people, people do a very simplistic calculation on, the dollars I spent and the dollars I pay. And they do it at the cost of electricity that I buy today without actually looking at, some of the vagaries. But There's also carbon dioxide foregone, and so there's a whole bunch of other things that are also important. So I think these are really interesting calculations for students to actually have a go at. So, yeah.
There was a question.
Is there any variation throughout years on the performance of geothermal?
Is there any variation?
During drought years, when there's a drought on, is there?
So for people online, the question was, is there any, do droughts matter? No. So it's completely irrelevant. So this is where it sort of gets interesting, and this is where we still have to develop some understanding about how these underground aquifers actually work. It does matter if you take the water out of the aquifer and you don't put it back in, because the replenishment of aquifers takes thousands of years. So in other words, it rains, a little bit trickles down, through the soil. It's got to travel, hundreds of meters to get into the aquifer. So if you take the water out and you don't put it back in, then can you deplete the aquifer? Absolutely. Are they doing that in Perth? Absolutely. So they've got a problem there because they don't, they water the gardens and do all sorts of things over there. If you go to Perth, you'll actually see that a lot of the gardens are rust coloured, so not surprisingly, they've got iron oxide in their underground aquifers. But at the moment, they're not replenishing them. So that matters because the replenishment rate is low. But a drought in and of itself is irrelevant. Okay.
Oh, we're really over time, yeah. Do we have any other questions for Rachel?
Just borrow your...
First of all, I'd just like to thank Rachel Webster so much for an absolutely incredible talk, actually. Shout out to Susie Shee for donating these books as gifts. Rachel, thank you so much.
thank you.
Thank you so much to everybody that attended in person and online. Just to let you know, coming up, we've already had that question. Coming up, we've got Dr. Suchi Yap in 2 weeks. So here in 2 weeks, she's going to talk to us about physics for cancer treatment. So particle accelerator technologies and radiation. And this is, I think, a relatively young-ish group in the School of Physics. And it's a huge, huge area. I think the statistics is like 1 in 3 people will be affected by cancer in their lifetime. So this is obviously something that's quite close, should be quite close to everybody, everybody's sort of consciousness. So this will be a fantastic talk. I don't think we've ever really had much on medical physics or the sort of physics before in the series. So I'm really, really encouraging you to come along to this. It's going to be great. Then we've got, of course, Professor Harry Quidey, our head of school, is going to talk to us about light and matter, and that will be on the 4th of September. And then our final lecture for this series for this year will be, of course, Professor David Jackson, who you will, of course, not be asking about nuclear power, or maybe you will, but certainly you can ask me about special relativity, and most of the time I think David tends to have lots of fun, whiz-bang, demonstrations and things. So please come along to those things. You'll be most welcome. And of course, there will be a feedback survey sent to you just like last time. So if you fancy filling that out for us, that would be fantastic. Thank you, everybody. And thank you again, Rachel.